72 hours ago, the European Space Agency released what they call the closest view yet of 3E Atlas, the interstellar object that's been captivating and terrifying the world in equal measure. Billions of dollars in space technology. 7 Mars orbiters positioned for the shot of a lifetime. And what did we get? A fuzzy white dot that looks like someone sneezed on a camera lens. Within minutes, social media erupted, not with wonder, but with rage. Amateur astronomers with backyard telescopes were capturing sharper images of comets millions of miles farther away. And yet NASA, with its Mars Reconnaissance Orbiter equipped with the most powerful camera ever sent to another planet, has gone completely silent. The government shutdown excuse is wearing thin, especially when you realize that the Chinese and UAE orbiters are also mysteriously quiet. By the time you finish listening to this, 3I Atlas will be less than a week away from disappearing behind the sun, hidden from every telescope on Earth during what should be its most active moment. And if Harvard physicist Avi Loeb is right, what happens next could change everything we thought we knew about what's possible in our cosmic neighborhood. If you're as fascinated by this mystery as I am, hit that like button and subscribe to stay updated as this story unfolds in real time. Tell me in the comments where you're listening from, what time it is there, and whether you think we're being told the complete truth about 3I Atlas. And if you want to help our community grow, share this on X, Facebook, Reddit, or your favorite messenger. Thank you for always having our back. Chapter 1, The Photo Drop That Broke the Internet. October 7th and 8th. 2025 will be remembered as the moment the space community collectively lost its patience. For months, we'd been building toward this. 3E Atlas, only the third confirmed interstellar object ever detected passing through our solar system, was making its closest approach to Mars. 7 different spacecraft from 4 space agencies were positioned to capture unprecedented images. The hype was real. Scientists promised us clarity, answers, maybe even proof of what this thing actually is. And then the images dropped. The European Space A's ExoMars Trace Gas Orbiter, positioned just 30 million kilometers from 3I Atlas, during its closest approach on October 3rd, released a series of images that can only be described as profoundly underwhelming. A fuzzy white dot moving slowly across a star field. No detail, no structure, nothing that would help us understand whether we're looking at a natural comet or something far stranger. The backlash was immediate and savage. Astronomy Vibes, a popular space commentary account on X, posted a side-by-side comparison that went viral within hours. On one side, a crisp, detailed image of Comet Lemon captured by an amateur astrophotographer with a simple mirrorless camera. On the other side, the ESA's image of 3E Atlas. The caption read, "If a simple mirrorless camera can catch Comet Lemon, why can't NASA capture 3E Atlas passing close to Mars?" The post currently has over 40,000 reposts and counting. But it was the follow-up that really struck a nerve. Billions in funding, and this is the best photo they've got. Looks more like a weather balloon in a foggy backyard. To understand why people are so angry, you need to understand what we were expecting versus what we got. The Cassis camera aboard the ExoMars Trace Gas Orbiter has an angular resolution of 11.36 microradians per pixel. At 30 million kilometers, that translates to 340 kilometers per pixel. For context, the estimated nucleus of 3I Atlas is somewhere between 5 and 46 kilometers across. That means the entire solid core of this object would occupy at best a fraction of a single pixel in these images. But here's where it gets interesting. The ESA knew this going in. They knew their cameras were designed to photograph the bright Martian surface from just a few hundred km away. Not faint objects tens of millions of kilometers distant. Nick Thomas, the principal investigator for the Cassis camera, admitted as much in the official statement. This was a very challenging observation for the instrument. The comet is around 10,000 to 100,000 times fainter than our usual target. So why release images they knew would be inadequate? Why build up expectations for months only to deliver something that provides zero new information? The official story is that they released what they had, that these represent the best possible images from the equipment available. But the timing feels deliberate, almost like a pressure release valve. Give people something, anything, to look at while the real data stays locked away. Because make no mistake, there are better images, much better images, and they're being held back. Chapter 2. The Missing Crown Jewel. While the ESA was releasing fuzzy dots, NASA's Mars Reconnaissance Orbiter was capturing something entirely different. The Hera camera, short for High Resolution Imaging Science Experiment, is the most powerful camera ever sent to another planet. Its resolution is so precise that from Mars orbit, it can distinguish objects the size of a kitchen table on the Martian surface. When 3i Atlas made its closest approach to Mars on October 3rd, Harris had a resolution of approximately 30 kilometers per pixel at the distance of the object. That's more than 10 times better than what the ESA cameras achieved. If there's any structure, any unusual features, anything that doesn't fit the natural comet narrative, HiRISE would have seen it. Avi Loeb, the Harvard physicist who's been tracking 3 Atlas since its discovery, put it bluntly in his latest blog post. The brightest pixel in the higher ice image will provide the best constraint yet on the area of 3 Atlas. We are all hoping that the HiRISIS team will release their images as soon as possible. That was written on October 7th. It's now October 8th. Still nothing. The official explanation is the United States government shut down. Over 15,000 NASA employees, more than 80% of the AWI's workforce have been furloughed. The AWI's website isn't being updated. Public communications have ceased. It's bureaucratic paralysis at the worst possible moment. But here's what doesn't add up. The ESA released their images. They're a European agency completely unaffected by American political dysfunction. China's Tianwen-1 orbiter was also positioned to observe 3i Atlas with its moderate resolution imaging camera. Also silent, the UAE's Hope orbiter equipped with the Emirates Exploration Imager had a clear shot as well. Nothing. Multiple space agencies, multiple sovereign governments with completely separate bureaucracies and priorities, all simultaneously unable or unwilling to release their best data on the most scientifically significant object to visit our solar system in years. The pattern is hard to ignore. Social media is ablaze with speculation. Some say coordination. Others say something was seen that requires careful review before public release. The more conspiracy-minded suggest the images show something so anomalous that releasing them without proper context would trigger mass panic. That last theory sounds absurd until you remember what's been happening over the past week with amateur observations. Because while the professional space agencies have been CI with their data, backyard astronomers have been capturing images that raise more questions than they answer. Chapter 3. When amateurs see what professionals won't show. On October 3rd, the exact day 3i Atlas made its closest approach to Mars, a Portuguese amateur astronomer operating under the username Dobsonian Power uploaded an image that immediately went viral. Using nothing more than a solar telescope from his backyard and some aggressive digital enhancement, he captured what appears to be an angular structure within 3 Atlas. Dark geometric shapes, protrusions that don't match the typical diffuse glow of a comet's coma. The caption, he added, was simple, but loaded with implication. What on earth is it within 6 hours? The image had been shared across every major astronomy forum, subreddit, and social media platform. The reaction split into two camps almost instantly. One group saw clear evidence of artificial structures, proof that 3E Atlas is not what mainstream science claims it to be. The other group dismissed it as classic pareidolia, the human tendency to see patterns where none exist, amplified by processing artifacts from inappropriate equipment. The debunkers had solid technical arguments. Solar telescopes use specialized filters designed for observing the sun's extreme brightness, not faint, deep space objects traveling at interstellar velocities. The equipment simply wasn't built for this kind of observation. Add aggressive digital enhancement to compensate for the inadequate setup, and you're essentially asking an algorithm to invent details that aren't really there. It's the astronomical equivalent of enhancing a blurry photo until you start seeing faces in the noise. But here's where the story gets complicated. Dasonian Power isn't some random internet conspiracy theorist with a cheap telescope and too much imagination. He's a respected amateur astronomer who's been sharing legitimate astrophotography work for over a decade. His YouTube channel features careful documentation of his equipment, his methods, his image processing workflows. This isn't someone trying to manufacture evidence for clicks. And when pressed on the anomalous structures in his 3i Atlas image, he didn't double down with wild claims. Instead, he acknowledged uncertainty. He promised to try again when the object becomes visible from Earth in early November after passing behind the Sun. His response was measured scientific, appropriately cautious, which makes the reaction to his image even more telling. Within 24 hours, multiple websites published articles specifically debunking his capture. Amateur telescope captures strange 3E Atlas image. Here's why it's not what it seems. The timing felt coordinated. The tone felt defensive, as if someone needed to quickly establish the narrative that nothing unusual had been photographed, that any apparent anomalies were merely technical artifacts before the image could gain too much traction. And then the enhancement wars began. Users across Reddit, Twitter, and various conspiracy forums started downloading the original ESA images and running them through their own processing algorithms. Some used standard astronomical image stacking techniques. Others employed AI upscaling tools designed for enhancing low-resolution photos. A few went full chaos mode with machine learning models trained to reconstruct fine details from limited data. The results varied wildly. Some showed nothing but slightly sharper versions of the same fuzzy dot. Others revealed what appear to be distinct geometric patterns, edges, structures that seem too regular to be natural ice and rock. The problem is that once you start aggressively processing an image, especially with AI tools, you're no longer looking at what's actually there. You're looking at what an algorithm thinks should be there based on its training data. If you train an AI on thousands of images of spacecraft and then ask it to enhance a blurry dot, it might very well invent spacecraft-like details because that's what it's learned to recognize. It's a scientific dead end wrapped in the illusion of clarity. But the proliferation of these enhanced images had an unintended effect. They muddied the water so thoroughly that distinguishing between legitimate amateur observations and outright fabrications became nearly impossible. Within 48 hours of the ESA photo release, there were dozens of supposedly enhanced versions circulating online. Some showed metallic surfaces. Others depicted what looked like solar panels or antennae or arrays. A few even included running lights and visible thrusters. Most were obviously fake digital art created by people with too much time and too much Photoshop skill. But mixed in with the noise were a handful of images that felt different, more subtle, less sensational images that showed just enough unusual regularity to make you wonder whether something real was being obscured by the flood of obvious hoaxes. Chapter 4. The 4chan leak that won't go away. On October 4th, an anonymous user on 4chan's paranormal board posted what they claimed was insider information about 3EE Atlas. The post was titled simply ESS Data Leak, and it began with a credential claim that was specific enough to sound legitimate, but vague enough to maintain anonymity. I'm a doctoral researcher working with the European Space Agency with continuous access to the combined observational data of 3R Atlas. Internet leaks are a dime a dozen. Most are easily dismissed as creative fiction or outright trolling, but this one was different. The level of technical detail was unsettling. The poster didn't make wild claims about alien invasions or secret military operations. Instead, they laid out a series of specific observational anomalies that, if true, would fundamentally challenge our understanding of what 3E Atlas actually is. The first anomaly, chemical impossibility. According to the post, spectroscopic analysis shows 3I Atlas is releasing approximately 100 kilograms of nickel gas per second, but with almost no iron emission. In normal stellar and planetary chemistry, nickel and iron are inseparable twins. They form together in supernova explosions. They travel together through interstellar space, and they appear together in comets and asteroids. Finding abundant nickel with virtually no iron is like finding smoke without fire. It violates basic assumptions about how matter behaves in natural cosmic environments. The second anomaly, thermal contradiction. The object is releasing massive amounts of gas and dust, the characteristic signature of an active comet being heated by the sun, but infrared observations show it remains cold, far colder than it should be given its outgassing rate and proximity to solar radiation. The poster compared it to watching someone sweat profusely in the freezer. The physics don't match the observation. The third anomaly, trajectory precision. The post referenced what Avi has been saying publicly, that 3 Atlas arrived with an orbital inclination of just 4.89 degrees relative to Earth's ecliptic plane. But the 4chan poster added something Lowe didn't emphasize. The trajectory isn't just unusual, it's a perfect straight shot from the direction of the galactic core. No wobble, no deviation, no signs of gravitational perturbation from nearby stars during its millions or billions of years travelling through interstellar space, as if it was aimed. Then came the part that elevated this from interesting speculation to something darker. The poster claimed the object fits the profile of what they called a post-biological entity, not a natural comet, not a conventional spacecraft, something in between. They described it as having a 3-phase particle engine with an estimated power output of 75 megawatt, continuously transmitting an active signal, and in their words, probing our solar system. The post concluded with a theoretical framework. The poster suggested 3E Atlas might be a macroscopic quantum object, specifically something called a Q-ball. It's an exotic theoretical construct from particle physics, a type of non-topological soliton that could theoretically exist at scales far larger than subatomic particles. If stable, a Q-ball could have properties that seem impossible under normal physics. It could be incredibly dense while appearing diffuse. It could absorb and redistribute energy instantaneously across its entire structure, explaining the thermal contradictions. It could even explain the nickel without iron problem if the Q-ball's internal quantum state preferentially produces certain isotopes. Within 18 hours, the post had been screenshot and shared across Reddit, Twitter, and dedicated UFO research forums. The conspiracy subreddit thread discussing it accumulated over 2,000 comments before moderators locked it for violating rules against unverified claims. But locking the thread didn't stop the conversation. It just moved it to other platforms, fragmenting into dozens of parallel discussions, each pulling the original post in different directions. Some focused on the chemical anomalies, others zeroed in on the Q-ball hypothesis. A few started connecting it to earlier claims about 3 Atlas potentially being the source of the 1977 WOW signal. Chapter 5, the 50000 km question. On October 4th, NASA's Perseverance rover sitting in Jezero crater on the Martian surface captured something in the night sky above. The image from its right navigation camera showed an elongated streak of light roughly 4 times longer than it was wide. At first glance, it looked like a typical long exposure capture of a moving object. Comets and asteroids often appear smeared in images when the camera tracks stars instead of the object itself. Standard stuff, except the math didn't work out that way. When people started calculating the apparent size of the streak based on Perseverance's known camera specifications and the distance to 3I Atlas at the time, they arrived at a disturbing number: 50,000 km long. That's not a comet nucleus. That's not even a comet with a tail. That's something else entirely. For comparison, Earth's diameter is less than 13,000 km. If this streak represented the actual physical size of 3E Atlas, we were looking at an object nearly 4 times wider than our entire planet. Social media exploded with speculation. Was 3 Atlas actually a massive cylindrical craft? Had it been masking its true size and shape this whole time behind a diffuse cloud of gas and dust? The timing felt significant. This image emerged just 1 day after the Mars flyby, right when all the professional space agencies went mysteriously quiet. Some saw it as confirmation that something deeply anomalous had been photographed, something that couldn't be easily explained away. The speculation reached high enough that Representative Anapolina Luna, a member of Congress known for her interest in unexplained aerial phenomena, reached out directly to Avi Loeb for his analysis. Think about that for a moment. A sitting member of the United States House of Representatives felt compelled to contact a Harvard physicist about a photograph from Mars. That's not normal protocol. That suggests someone in official channels was concerned enough to want expert interpretation outside the usual NASA communication pipeline. Lowe's response was thorough and on the surface reassuring. He calculated that the Perseverance NavCam has an angular resolution of 0.33 milliradians per pixel. At the distance of 3I Atlas, when the image was taken approximately 38 million kilometers, that translates to about 12,500 kilometers per pixel. The streak in the image spans roughly 4 pixels, which gives you that 50,000 km length. But Lowe argued this was an artifact of composite imaging. The streak wasn't showing the actual size of 3 Atlas. It was showing the path the object traced across the Martian sky during a long integration time, likely around 10 minutes of stacked exposures. His reasoning was solid. Mars orbits the Sun at 24 km per s. 3I Atlas was travelling at 67 km per s relative to the Sun in the opposite direction, giving it a relative velocity of over 90 km per s compared to Mars. Over 10 minutes. That's exactly 54,000 km of travel, perfectly matching the observed streak length. The shape wasn't the object. It was the object's motion smeared across time. Case closed. Right. The cylinder theory debunked by basic physics and careful math. Except Lowe included one sentence in his analysis that conspiracy theorists latched onto like a lifeline. He wrote, "If the NavCam images represent single snapshots with an exposure time below 3.228 seconds, then the brightness and angular length of the observed source imply that it is not 3I Atlas. In that case, the source might be much closer to the camera, capable of being smeared into an elongated image with a smaller spatial size and smaller speed. Wait, if these are single-frame captures, then what Perseverance photographed wasn't 3 Atlas at all. It was something else. Something closer to Mars. That qualifier opened a door that no amount of subsequent clarification could fully close. Because NASA hasn't confirmed whether the image is a composite or a single frame. They haven't released the metadata. They haven't provided the exposure time or the number of stacked images. The government shutdown excuse applies here too. No staff to process requests. No one available to confirm basic technical details about how the image was captured. Chapter 6. 48 Years of Silence. August 15th, 1977. Ohio State University's Big Ear radio telescope detected a 72-second burst of radio energy so unusual, so perfectly structured that astronomer Jerry Ayan circled it on the printout and wrote one word in red pen. Wow. For nearly 5 decades, that signal has remained one of the greatest mysteries in the search for extraterrestrial intelligence. It came from the direction of Sagittarius near the constellation's densest star fields. It was narrowband, focused at one specific frequency, and it has never repeated. Hundreds of follow-up observations, thousands of hours of listening time pointed at the same region of sky. Nothing. Just that one burst 48 years ago. And then eternal silence until Avi ran the numbers on 3 Atlas. He calculated where the object was on August 12th, 1977, just 3 days before the WOW signal was detected. The answer: approximately 600 astronomical units from Earth, roughly 600 times the distance between Earth and the Sun. But more importantly, he calculated what direction 3EI Atlas was coming from at that time. Right ascension 19 hours 40 minutes, declination 19 degrees. The WOW signal came from right ascension 19 hours 25 minutes, declination negative 27 degrees. The two directions are separated by approximately 9 degrees. In the vastness of space, with random objects coming from literally any possible direction, the probability of this alignment is about 0.6%. Not impossible, but deeply suspicious. Lowe didn't stop there. He asked the next logical question. If 3i Atlas sent the WOW signal from 600 astronomical units away, how powerful would the transmitter need to be? The math is straightforward. The detected intensity was between 54 and 212 Jansky across a 10K bandwidth. At 600 AU distance, that corresponds to a transmitter output between half a gigawatt and 2 gigawatts. For reference, a typical nuclear reactor on Earth produces about 1 gigawatt. So, we're talking about nuclear power plant levels of energy focused into a narrow radio beam. Not impossible for an advanced civilization. Actually, quite reasonable if you're trying to send a detectable signal across interstellar distances without wasting energy on omnidirectional broadcasting. There's another detail that makes the connection harder to dismiss. The WOW signal was observed at a frequency of 1/420.4 5564,556 MHz blue, shifted by approximately 10 km per s toward Earth relative to the hydrogen line. That blue shift indicates the source was moving toward us. 3i Atlas is currently approaching the Sun at about 60 km per s. Lowe suggests that if this object has maneuvering capability, it could have been moving slower in 1977, then accelerated after detecting habitable zone planets in our solar system. A reconnaissance pulse. A radar scan checking for signs of technological civilization before committing to a closer approach. Here's what makes this entire connection so frustrating. It would be trivially easy to check. Point a radio telescope at 3i Atlas. Listen at the hydrogen line frequency. If it's transmitting, we'll know within hours. If it's silent, the WOW signal connection is probably coincidental. Simple test. Definitive answer. And yet, as Lowe noted in his latest blog post, not a single radio telescope has reported data on 3i Atlas. The Very Large Array hasn't looked. The Arecibo telescope is destroyed. The Green Bank telescope hasn't published observations. Even SETI, the organization literally dedicated to finding extraterrestrial signals, hasn't publicly announced any monitoring efforts. The silence from the radio astronomy community is deafening. Chapter 7. The Path That Shouldn't Exist. Imagine throwing a dart at a globe from across a room while blindfolded. Now imagine that DART not only hits the globe, but lands within a few degrees of the equator. That's roughly the statistical improbability we're dealing with when we look at how 3E Atlas entered our solar system. Objects coming from interstellar space can arrive from literally any direction. They should be randomly distributed across the celestial sphere, coming in at all possible angles. And yet 3-2 Atlas arrived with an orbital inclination of just 4.89 degrees relative to Earth's ecliptic plane less than 5 degrees. That puts it in less than 1% of possible arrival angles. Avi Loeb has been hammering this point in every interview, every blog post, every public statement since July. The trajectory is anomalous, not just unusual, statistically profoundly unlikely for a random interstellar object. To understand why, you need to think about how objects move through the galaxy. Stars in the Milky Way disk orbit the galactic center with some average velocity, but they also have random motions up and down, side to side, like bees swarming around a hive. That randomness means objects ejected from other star systems should arrive at our solar system from all directions with roughly equal probability. There's no preferred direction, no cosmic highway that funnels interstellar visitors into our ecliptic plane. And before someone suggests that maybe objects from the Milky Way disk naturally arrive at shallow angles, Lowe addressed that. 2. The galactic disk itself is tilted about 60 degrees relative to our solar system's ecliptic plane. 60 degrees. That's more than 10 times larger than the inclination of 3 Atlas. If this object came from a typical star system in the galactic disk and was ejected randomly, we'd expect it to arrive at a steep angle, not a shallow one. The alignment is backwards from what galactic geometry would predict. Compare 3 Atlas to the only other interstellar objects we've detected. Oumuamua, discovered in 2017, arrived with an inclination of 123 degrees, wildly tilted coming in from above the solar system plane. 2I Boris, spotted in 2019, had an inclination of 44 degrees, still steep, still consistent with random arrival from interstellar space. Both of those objects behaved exactly as expected for natural interstellar visitors. 3 Atlas is the outlier, the anomaly, the one that doesn't fit the pattern. Lowe calculated the probability of this alignment assuming random directions less than 1% chance. Some colleagues pushed back, suggesting maybe his statistics were too conservative, maybe the true probability is closer to 5 or 10% when you account for various selection effects and observational biases. Fine. Even at 10%, you're still looking at something that should only happen once in every 10 interstellar objects we detect. And we've only detected 3. The odds of the third one being the rare exception rather than the rule are not in favour of coincidence. Now layer that on top of everything else. The WOW signal alignment also less than 1% probability. The chemical anomalies with nickel but no iron, the thermal contradictions, the missing high-resolution images from multiple space agencies, the government shutdown happening at the exact moment we need NASA most. Any single one of these things could be explained away. Coincidence, measurement error, bureaucratic incompetence. But when you start stacking anomalies, when you start multiplying small probabilities together, the compound improbability becomes harder to dismiss. There's a principle in statistics called the prosecutor's fallacy. It's the mistake of treating multiple independent low-probability events as if they're related when there are actually just random coincidences that happen to cluster together. If you flip a coin enough times, eventually you'll get 10 heads in a row. It doesn't mean the coin is rigged, it just means you flipped it enough times for unlikely sequences to occur. Skeptics will argue that's what we're seeing with 3I Atlas. A natural comet that happens to have several unusual but ultimately explainable properties that coincidentally appeared together in the same object. Unlikely? Sure, but not impossible. The counter-argument is equally valid. If something walks like a duck, quacks like a duck, swims like a duck, and has duck DNA, at some point you have to consider the possibility that it might actually be a duck. Or, in this case, if an object arrives on a statistically unlikely trajectory, shows chemical signatures that don't match natural processes, correlates with a 48-year-old unexplained radio signal, and prompts multiple governments to withhold their best imaging data, maybe it's worth seriously considering that we're not looking at a random chunk of ice and rock from another star system. Chapter 8. When questions become dangerous. Something strange started happening around October 5th. Users across multiple platforms began reporting that their posts about 3 Atlas were disappearing, not being flagged or marked as misinformation, actually vanishing. A Reddit user documented posting a detailed thread analysing the chemical anomalies from the alleged ESA leak. The thread gained traction, accumulated hundreds of upvotes and dozens of comments within 2 hours. Then it was gone. Not removed with a moderator explanation, just deleted from existence. When the user tried to repost, the submission wouldn't go through, shadow banned without notification or explanation, on Twitter, now X. Several accounts noticed similar patterns, astronomy vibes. The account that went viral criticising the ESA photos reported significant engagement drops after October 7th. Posts that would normally reach tens of thousands of people were suddenly plateauing at a few hundred views. No official restrictions, no warning messages, just algorithmic suppression, quiet enough to be deniable, but aggressive enough to be effective. Other creators in the space astronomy community noticed the same thing. Videos about 3 Atlas that would typically perform well were getting a fraction of their usual reach. YouTube presented a different problem. Content creators who posted analysis videos speculating about 3.2 Atlas began receiving demonetization notices. The stated reason varied. Some were flagged for discussing sensitive topics without proper context. Others were categorized as potentially misleading content about scientific matters. A few got hit with the vague but ominous label of content that may not be suitable for all advertisers. The pattern was clear. You could make a video saying 3I Atlas is definitely just a comet and mainstream science has it figured out. That was fine. Monetized, promoted, but suggest there might be anomalies worth investigating. Suddenly your video becomes advertiser unfriendly. Facebook's approach was the most overt. The platform's fact-checking system, operated by third-party verification organizations, started aggressively labeling 3 Atlas content. Posts sharing the 4chan leak got slapped with missing context warnings. Claims about the trajectory anomalies were flagged as partly false, even when the post were just quoting Avi Loeb's published calculations verbatim. The fact-check articles offered reassurance. Space agencies confirm no threat from interstellar comet. Experts say unusual features likely natural processes. The subtext was clear. Don't worry, don't speculate. Trust the authorities, move along. The timing felt coordinated. All of this ramped up within 48 hours of the ESA photo release. Writer public frustration was peaking over the lack of quality images. It's the kind of pattern that makes conspiracy theorists feel vindicated and makes skeptics roll their eyes at overreach paranoia. Because here's the thing, social media platforms suppress content all the time. Algorithms change, engagement fluctuates, fact-checkers flag misinformation. These are normal platform operations, not evidence of coordinated censorship unless there's a pattern, unless it's all happening at once, targeting one specific topic. Right at the moment when public interest is highest and official answers are most absent, some creators started using coded language to avoid suppression. Instead of 3E Atlas, they'd say the visitor or the object. Instead of alien or extraterrestrial, they'd use non-terrestrial or anomalous. It was like watching people develop a new vocabulary to discuss something the platforms didn't want discussed openly. The Strand effect in real time. The more the content got suppressed, the more people assumed there was something worth hiding. The more aggressively fact-checkers pushed back, the less people trusted the official narrative. Every attempt to manage the conversation just amplified the suspicion that the conversation needed to be managed. Chapter 9. The Moment We Can't Watch, October 29th and 30th. Mark those dates. In less than 72 hours from now, 3I Atlas will reach perihelion, its closest approach to the Sun. It will pass at a distance of approximately 202 million kilometers, just inside the orbit of Mars. For a natural comet, this is the moment of truth. The intense solar radiation at that distance should cause dramatic outgassing, possibly even fragmentation. We've seen it happen before. Comets get close to the Sun. The heat becomes too much, and they break apart into pieces. Spectacular when it happens. And if 3 Atlas is just an ordinary chunk of ice and rock from another star system, that's exactly what should occur. But here's the problem. We won't be able to see it. 3 Atlas will be on the opposite side of the Sun from Earth during its perihelion passage. Every ground-based telescope on our planet will be useless. The object will be lost in the solar glare, completely hidden from observation during what should be its most active and revealing moment. Some are calling it unfortunate timing. Others see it as suspiciously convenient. If you wanted to do something without being watched, you couldn't pick a better window. Avibe has been explicit about what happens next. In his October 3rd blog post published on the day of the Mars flyby, he laid out 2 scenarios. If 3 Atlas is a natural comet, it may erupt in a flare of outgassing or break up into icy fragments soon. The sunlight will deposit gouts of power onto its surface. That energy has to go somewhere. For ice and rock, it goes into vaporization, sublimation, possibly structural failure. But then Lowe added the alternative. Alternatively, if it is technological, it may maneuver to benefit from the Sun's gravitational assist or release probes that could intercept the Earth or other planets owing to its retrograde orbit opposite in direction to the motion of the planets around the Sun. Read that again. Release probes that could intercept Earth. He's not talking about passive observation anymore. He's talking about active deployment. The retrograde orbit is key here. 3 Atlas is moving opposite to the direction planets orbit the Sun. That means any probe it releases doesn't have to fight against planetary motion to reach us. It can simply drop into an intercept trajectory and let orbital mechanics do the work. From behind the Sun, hidden from our view, it would be trivial to launch something toward Earth that wouldn't be detected until it was already close. Lowe went further. He wrote, "When you look at the Sun in the coming weeks, keep in mind that 3 Atlas is passing behind it. If 3 Atlas will maneuver towards Earth when it reappears on the other side of the Sun, the financial markets may crash. Financial markets may crash." That's not metaphor. That's not hyperbole. He's suggesting that if this object demonstrates technological capability, if it alters course toward Earth after perihelion, the economic and social consequences would be immediate and severe. Stock markets respond to uncertainty. The uncertainty of a potentially hostile interstellar object actively changing its trajectory toward our planet would be existential level uncertainty. The timing of everything compounds the tension. The government shutdown means NASA is offline during the critical observation window. The best images from the Mars flyby are still unreleased. Amateur astronomers can't observe the object for the next month because it's behind the Sun. Radio telescopes haven't checked for transmissions. We're flying blind into the most important moment of this entire encounter. And whether through incompetence or design, we've created a situation where we won't know what 3I Atlas does at perihelion until it's already done it. There is one group watching, the Galileo project led by Lowe himself. operates 3 observatories, one in Massachusetts, one in Pennsylvania, one in Nevada. They're equipped with high-resolution cameras, infrared sensors, and radio receivers designed specifically to detect anomalous aerial phenomena. During late October and early November, all 3 observatories will be in maximum operational mode, monitoring the skies for anything unusual. If 3I Atlas releases probes, if there's enhanced UAP activity correlated with its perihelion passage, the Galileo instruments might catch it, might being the operative word. 3 observatories covering a small fraction of Earth's sky. If something comes and it avoids those specific observation zones, we'll miss it entirely. Chapter 10. What comes after early November? That's when 3I Atlas will emerge from behind the Sun and become visible again from Earth. Ground-based telescopes will be able to track it once more. We'll see whether it survived perihelion intact or broke apart under solar stress. We'll measure its trajectory to determine if any course corrections occurred, and we'll finally know whether the past 4 months of speculation, conspiracy theories, and unanswered questions were justified or just collective hysteria over a completely natural interstellar visitor. If 3E Atlas emerges on the same trajectory it entered with, if it shows clear signs of fragmentation or increased outgassing consistent with solar heating, if it behaves exactly like 2I Borisov did during its solar approach in 2019, then the mystery is essentially solved. Natural comet, unusual chemistry, sure, statistically unlikely trajectory granted, but ultimately just an icy remnant from another star system passing through ours. The WOW signal connection becomes coincidence. The 4chan leak becomes creative fiction. The missing NASA images become bureaucratic delays during a government shutdown. Everything slots back into the comfortable framework where interstellar objects are interesting but not alarming. But if it doesn't, if 3E Atlas emerges with an altered trajectory, if it demonstrates even subtle course corrections that can't be explained by outgassing thrust, if radio telescopes finally point at it and detect structured transmissions, if the NASA images eventually surface and show geometric structures that shouldn't exist on a natural object, then we're in completely uncharted territory, not just scientifically, socially, politically, economically. Every assumption about our place in the cosmos gets challenged. Every government's response to the question of extraterrestrial contact gets tested in real time. Aviby created something he calls the Loeb scale. It's a ranking system for how likely an object is to be of artificial origin and how much of a potential threat it represents. Rank 1 means almost certainly natural with interesting but explainable anomalies. Rank 10 means definitely artificial with demonstrated hostile intent and capability to reach Earth. He stated publicly that he won't rank 3I Atlas lower than a 2. Even in the best-case scenario, the anomalies are too persistent, too numerous, too correlated. A 2 means probably natural, but with enough unexplained features to warrant serious investigation. It means we can't definitively rule out artificial origin without more data. That's where we are right now, suspended between probable natural object and possible technological artifact, waiting for November, waiting for the high-resolution images that may never come, waiting for radio observations that haven't happened, waiting for 3I Atlas to either continue on its hyperbolic trajectory out of the solar system, never to be seen again, or to do something that forces us to confront the reality that we are not alone and we are not ready. The ESA has announced that their Jupiter Icy Moons Explorer spacecraft JUICE will observe 3I Atlas between November 2nd and 25th using various instruments. This will happen just after perihelion when the object should be in its most active state. The data won't be available until February 2026 due to communication delays and processing time. 7 months of waiting for images that were captured in November. 7 months of not knowing whether the enhanced activity JUICE observes is normal cometary outgassing or something else entirely. 7 months of wondering whether that fuzzy dot the ESA showed us in October was really the best they could do, or whether they're carefully managing a revelation they don't know how to deliver. Whatever 3i Atlas is, whatever it does in the coming weeks, the conversation around it has already revealed something important about where we are as a civilization. We don't trust our institutions to tell us the truth about something this significant. We don't believe the official reassurances. We see patterns in the timing of shutdowns and data delays that may or may not be real. We're primed for conspiracy because we've learned, sometimes the hard way, that conspiracy is not always theory. Sometimes it's just early reporting on what later becomes confirmed fact. Chapter 1. The Invisible Visitor. On the 1st of October 2025, something the size of a giraffe passed between Earth and our satellites. It came closer to our planet than the International Space Station orbits. We had no idea it was coming. By the time astronomers spotted it, asteroid 2025 TF had already gone, slipping back into the darkness of space like a shadow that forgot to announce itself. Think about that for a moment. We live in an age where we can photograph distant galaxies forming billions of years ago. Yet, a rock close enough to practically scratch our atmosphere went completely unnoticed until it was already in our rearview mirror. If you find that as unsettling and fascinating as I do, consider liking and subscribing to stay updated on these cosmic close calls and the mysteries unfolding above us. Tell me in the comments where you're listening from, what time it is there, and whether you think we should be more worried or more amazed by how much we still miss in the night sky. And if you want to help our community grow, share these videos on X, Facebook, Reddit, or your messenger. Thank you for always having our back. The asteroid measured somewhere between 1 and 3 m wide, small enough that had it actually entered our atmosphere, it would have burned up as a brilliant fireball. Nothing that would threaten cities or civilizations. But here is what keeps astronomers awake at night. If we cannot reliably detect something this close, something travelling at speeds that would cross the distance from New York to Los Angeles in less than a minute, what else might we be missing? The European Space Agency and NASA track thousands of near-Earth objects, carefully cataloguing which ones pose the greatest risk of collision. To be classified as potentially hazardous, an asteroid must measure at least 140 m in diameter and follow an orbit that brings it within 7.5 million kilometers of Earth, roughly 20 times the distance between us and the Moon. Asteroid 2025, TF falls far short of that size threshold, which partly explains why it evaded detection. Our telescopes and survey systems prioritize finding the big ones, the civilization enders, the objects that could create another extinction event if they struck at the wrong angle. But this tiny visitor reminds us that space is not empty. It churns with debris, ancient fragments from the formation of our solar system, pieces of shattered worlds that never quite became planets, remnants of collisions that happened when Earth itself was young. Most of this material stays far away, locked in stable orbits in the asteroid belt between Mars and Jupiter, or drifting in the distant Kuiper belt beyond Neptune. But gravitational interactions, the subtle tugs of Jupiter's immense mass or the nudge from a passing comet can shift these orbits, sending rocks on new trajectories that sometimes intersect with ours. What makes 2025 TF particularly interesting is not just that it came close, but that it came close during a month when the sky seems unusually busy with visitors. Chapter 2. The Brightening Wanderer. While one cosmic traveller slipped past us unannounced, another is making a much more theatrical entrance. Comet C 2025, a 6 better known as Lemon after the observatory that discovered it, is brightening in our October skies. Astrophotographers around the world have been capturing increasingly dazzling images as this ball of ancient ice and dust makes its way toward a close approach with Earth. Unlike the stealth asteroid that surprised us, Lemon has been tracked carefully since its discovery, and right now it sits at the edge of naked eye visibility. Over the next few weeks, if conditions are right and skies are dark enough, you might be able to step outside and see it yourself. A faint smudge of light with a ghostly tail stretching away from the sun. Comets are fundamentally different from asteroids. Where asteroids are rocky or metallic solid chunks of material that formed in the warmer inner solar system, comets are icy bodies that originated in the cold outer reaches. They're sometimes called dirty snowballs, though that description sells them short. A comet nucleus contains frozen water, carbon dioxide, methane and ammonia mixed with dust and organic compounds, the chemical building blocks of life. As a comet approaches the sun, solar radiation warms its surface, causing the ice to sublimate, turning directly from solid to gas without becoming liquid first. This creates the coma, a temporary atmosphere of gas and dust that can stretch for hundreds of thousands of kilometers. Solar wind and radiation pressure push this material away from the nucleus, forming the characteristic tail that always points away from the sun. Regardless of which direction the comet is travelling, Lemon is not the only comet gracing our skies this month. Another visitor, C2025R2 known as Swan, slides past Earth later in October at a distance of 0.26 astronomical units, close enough to put on a show for those with binoculars or small telescopes. Both comets currently shine at around magnitude 6, right at the threshold of human vision under perfect conditions. But comets are notoriously unpredictable. They can suddenly brighten if their rotation exposes fresh ice to sunlight, or if an outburst sends a plume of material into space. They can also fragment, breaking apart under the stress of solar heating or tidal forces, creating multiple nuclei that each develop their own coma and tail. What draws people to watch comets beyond their beauty is their connection to deep time. The ice in these objects formed billions of years ago in the outer solar system, preserved in a cosmic freezer far from the sun's warmth. When we see a comet, we are seeing material that existed before Earth had oceans, before the moon was fully formed, before life emerged in whatever warm tidal pool or deep-sea vent first gave rise to self-replicating chemistry. Some scientists believe that comets delivered significant amounts of water to early Earth, raining down in a bombardment that helped fill our oceans. Others suggest that the organic molecules found in comets, including amino acids, the building blocks of proteins, may have seeded our planet with the raw materials needed for life to begin. This connection between ancient comets and the origin of life brings us to another discovery that has scientists reconsidering how common the ingredients for life might be across the universe. Chapter 3. A Nursery for Moons, 625 light-years from Earth. Something remarkable is happening around a young planet. The James Webb Space Telescope has captured the first direct measurements of a moon-forming disk, a rotating ring of gas and dust surrounding an exoplanet called CTB, and within that disk, Webb detected the chemical signatures that could give rise to moons: hydrogen cyanide, acetylene, benzene, propan, ethane, carbon dioxide, all carbonary molecules swirling in a structure that looks hauntingly familiar to planetary scientists who study our own solar system's history. This matters because for decades we have theorized about how moons form, but we've never actually watched it happen. Jupiter's 4 largest moons, the Galilean satellites discovered by Galileo in 1610, orbit their planet in a flat plane, suggesting they condensed from a disk of material surrounding Jupiter billions of years ago, much like the planets formed from a disk around the young Sun. The 2 outermost of these moons, Ganymede and Callisto, are 50% water ice, though they likely have rocky cores of carbon or silicon beneath their frozen shells. Looking at their orbits and compositions, scientists have long suspected that a circumplanetary disk once existed around Jupiter, and within that disk, the raw materials for moon formation gathered and coalesced. Now, with CTRB, we can see a similar process unfolding in real time. Though we have to remember that real time in astronomical terms is a bit misleading. The light we detect from this system left 625 years ago when Earth was in the midst of the Renaissance, and no one had yet conceived of planets beyond our own solar system. But from our perspective, we are witnessing moon formation as it happens, and the details are fascinating. The planet itself orbits a star that is only 2 million years old, still accreting material from its own circumstellar disk. This means we are seeing a system in its infancy, a planetary nursery where multiple generations of structure formation occur simultaneously. What surprised researchers most was the stark chemical difference between the planet's moon-forming disk and the star's planet-forming disk. The circumplanetary disk around CTRB is rich in carbon-bearing molecules, but shows no signs of water. Meanwhile, the circumstellar disk around the star contains water, but lacks the carbon chemistry seen in the planet's disk. This chemical segregation happened in just 2 million years, suggesting that disk chemistry evolves rapidly and follows different paths depending on local conditions. Temperature, radiation levels, the presence of magnetic fields, all of these factors influence which molecules can survive and which get broken apart. The implications stretch beyond understanding how moons form. If we can map the chemistry of these disks in young systems, we can start to predict which exoplanets might host moons and which of those moons might have conditions suitable for life. In our own solar system, some of the most promising places to search for life are not planets, but moons. Europa orbiting Jupiter likely has a liquid water ocean beneath its icy crust, kept warm by tidal heating from Jupiter's gravitational pull. Enceladus, a small moon of Saturn, shoots geysers of liquid water into space from an underground ocean, and within those geysers, scientists have detected organic molecules. If moons around other stars form with similar characteristics, then the number of potentially habitable worlds in the galaxy multiplies dramatically. We would need to look not just at planets in the habitable zone around their stars, but at moons around giant planets anywhere in a system. This expanding view of where life might arise connects to technologies we are developing here on Earth. Technologies that might one day help us reach these distant worlds, or at least understand them better. Chapter 4. The Quantum Leap. The United Nations has designated 2025 as the International Year of Quantum Science and Technology, marking 100 years since the initial development of quantum mechanics. It is fitting timing because 2025 is shaping up to be the year when quantum computing shifted from laboratory curiosity to something approaching practical reality. In November of 2024, Microsoft and Atom Computing announced they had successfully created and entangled 24 logical qubits, a technical achievement that represents a major step toward building quantum computers that can actually solve useful problems. To understand why this matters, we need to talk about what makes quantum computers different from the device you're using to listen to this right now. Classical computers, whether they're smartphones or supercomputers, process information using bits, units that represent either 0 or 1, on or off, true or false. Everything your computer does, from streaming video to running complex simulations, comes down to manipulating enormous numbers of these binary digits at incredible speed. Quantum computers operate on fundamentally different principles. Instead of bits, they use qubits, quantum bits, which can exist in a superposition of states, simultaneously representing 0 and 1 until they're measured. This is not just a metaphor or a trick. At the quantum scale, particles genuinely exist in multiple states at once, a consequence of the wave-like nature of matter described by quantum mechanics. When you have multiple qubits in superposition, they can represent exponentially more information than the same number of classical bits. 2 classical bits can represent 4 possible values, 0, 0, 1, 1, 0, or 1, 1, but only one at a time. 2 qubits in superposition can represent all 4 values simultaneously. 3 qubits can represent 8 values at once. The scaling continues exponentially, which means a quantum computer with just a few hundred qubits could theoretically perform calculations that would take classical supercomputers longer than the age of the universe. But there's always been a catch. Qubits are extraordinarily fragile. They lose their quantum properties, a process called decoherence. When they interact with their environment, temperature fluctuations, stray electromagnetic fields, even cosmic rays passing through the lab can cause errors. This is why quantum computers must be cooled to temperatures near absolute zero and shielded from external interference. Even then, errors accumulate so quickly that calculations become unreliable before you can finish them. The breakthrough that makes 2024 and 2025 so significant is progress in quantum error correction. The ability to detect and fix these errors without destroying the quantum state you're trying to preserve. Creating 24 entangled logical qubits means creating qubits that you have built-in error correction, making them far more stable and reliable than the physical qubits that make up the raw hardware. Entanglement is another quantum phenomenon that Einstein famously called spooky action at a distance. When qubits are entangled, measuring the state of one instantaneously affects the state of the others regardless of the distance between them. This allows quantum computers to perform certain types of calculations like searching databases or factoring large numbers far more efficiently than classical computers ever could. The race to build practical quantum computers is now global and intensely competitive. In early 2025, Japan announced a $7.40 $4 billion investment in quantum technology. Spain committed $900 million. These investments bring total public financing for quantum research beyond $10 billion, a signal that governments see quantum computing not just as a scientific curiosity, but as a strategic technology that could reshape everything from drug discovery to cryptography to artificial intelligence. The private sector is equally invested. Companies like Google, IBM, and Amazon continue to push the boundaries of what is possible. Google has claimed its quantum processors can solve certain problems exponentially faster than classical supercomputers. IBM has laid out a roadmap to build a system with 200 logical qubits by 2028. Meanwhile, startups are exploring alternative approaches using photons instead of superconducting circuits or trapped ions instead of solid-state devices. Each method with its own advantages and challenges. But beyond the engineering achievements, there is something almost philosophical about quantum computing that captures the imagination. These machines operate according to principles that defy our everyday intuition about how reality works. And yet those principles appear to be fundamental to the universe itself. The same quantum mechanics that makes qubits possible also governs the behavior of atoms, the structure of molecules, the emission of light from stars. In a sense, quantum computers are allowing us to harness the native language of the universe to solve problems that would otherwise remain intractable. One of those problems is understanding and controlling the process of nuclear fusion, which brings us to another set of breakthroughs that happened in the same time frame. Chapter 5: Capturing the Stars. On February 12, 2025, scientists at the West Tokamak reactor in France set a new world record. They maintained blisteringly hot plasma for 22 minutes and 17 seconds, a duration that surpassed the previous record by over 4 minutes. The plasma reached 50 million degrees C, roughly 3 times the temperature at the core of the Sun. This might not sound like progress to those unfamiliar with fusion research. After all, the Sun has been maintaining fusion reactions for 4.5 billion years without human intervention, but creating and controlling a star-like process here on Earth is one of the most difficult challenges in all of science and engineering. Fusion works by forcing atomic nuclei together so tightly that they overcome their natural electromagnetic repulsion and merge, releasing energy in the process. In the Sun, this happens because the immense mass of the star creates crushing gravitational pressure at its core, along with temperatures of 15 million degrees. On Earth, we lack that gravitational advantage. So, we need even higher temperatures to achieve fusion, and we need some way to contain plasma that hot without it touching any physical surface, since no material can withstand such temperatures without vaporizing instantly. The solution is magnetic confinement. Tokamaks use powerful magnetic fields to create a cage of force that holds the plasma in a donut-shaped region suspended in vacuum, never touching the walls. The West reactor's achievement of 22 minutes is significant because future fusion power plants will need to operate continuously, not in short bursts. You cannot economically generate electricity if your reactor has to shut down and restart every few minutes. The record demonstrates that the engineering challenges of steady-state operation, of managing heat flow, of keeping the plasma stable against instabilities that can disrupt the magnetic confinement, are slowly being solved. The previous record of just over 17 minutes belonged to China's East Tamak, achieved in January of 2025, meaning we have seen 2 major milestones in plasma duration within weeks of each other. These are not the only fusion breakthroughs happening right now. ETA Technologies, a private fusion company, announced in April 2025 that they had achieved a major simplification in how they form and stabilize their plasma. Their approach uses something called a field-reversed configuration, or FRC, a magnetic structure that is more compact than a traditional tokamak. Previously, creating an FFRC required elaborate formation sections at either end of the machine where plasma was generated and then accelerated and collided at high speed in the center. TA figured out how to create heat and stabilize an FFRC plasma directly in the center of their device using only neutral beam injection, eliminating the complex formation hardware. This reduces cost, increases efficiency, and brings them closer to demonstrating net energy gain before the end of the decade. Meanwhile, the private fusion sector as a whole is expanding rapidly. Commonwealth Fusion Systems is building a pilot plant called Spark outside Boston, scheduled to come online in 2027. Helon has completed initial tests on their latest machine designed to achieve break-even using a different magnetic confinement scheme. General Fusion, based in Canada, is building a demonstration system that uses a completely different approach. Mechanically compressing plasma rather than relying purely on magnetic fields. The diversity of approaches reflects both the difficulty of the problem and the recognition that there may be multiple paths to successful fusion energy. In December of 2020, 2 scientists at the National Ignition Facility achieved fusion ignition for the first time, a reaction that produced more energy than the lasers delivered to ignite it. That was a scientific milestone, proof that controlled fusion is physically possible. But turning that proof of concept into a power plant requires solving countless engineering challenges. Fusion fuel, typically a mixture of deuterium and tritium, both isotopes of hydrogen, must be continuously supplied. The neutrons produced by fusion reactions carry enormous energy and make the reactor walls radioactive, so materials need to withstand years of neutron bombardment without degrading. The heat generated must be captured efficiently and converted to electricity. and all of this must happen at a cost that competes with other energy sources. What makes fusion so tantalizing despite these challenges is the promise of nearly limitless clean energy. Deuterium can be extracted from seawater, where it exists naturally as one atom in every 6,500 hydrogen atoms. At that concentration, the oceans contain enough deuterium to power human civilization for millions of years. Tritium is rarer and must be bred from lithium, but lithium is relatively abundant. Fusion produces no long-lived radioactive waste like fish reactors do. It produces no carbon emissions, and a fusion reactor cannot melt down or explode because the plasma is so tenuous that any disruption causes the reaction to simply stop. The question is no longer if fusion will work, but when it will become practical and economical. Optimists point to the rapid progress in both government and private sector projects and suggest we could see the first commercial fusion electricity on the grid by the early 2030s. Skeptics note that fusion has been perpetually 20 years away for the past 60 years and caution that unexpected problems always arise. But the momentum in 2025 feels different, driven by a combination of technological breakthroughs, massive investment, and the urgent need for clean energy sources to address climate change. For the first time, it seems plausible that a child born today might grow up in a world where fusion power is as common as solar panels or wind turbines. And perhaps the child's generation will use fusion-powered spacecraft to explore the solar system, following the trails of those ancient comets and asteroids and investigating the planets and moons we've only glimpsed from afar. One of those moons, Mars, continues to surprise us with hints that it once might have hosted life. Chapter 6: Leopard Spots on Mars. In July of 2024, NASA's Perseverance rover drilled a core sample from a rock nicknamed Char Falls in Mars' Jezero crater. The rock showed features that mission scientists described as the most puzzling, complex, and potentially important they had encountered. After a year of rigorous peer review, the findings were published in the journal Nature in September of 2025, and they represent the strongest evidence yet that Mars might have once been home to microbial life. The key word there is might, because one of the hardest lessons in astrobiology is that nothing is ever as simple as it first appears. Java Falls sits in an ancient riverbed within a region Perseverance has been exploring called Bright Angel. Billions of years ago, water flowed through this area, carving channels as it rushed into Jezero crater, which at the time was a lake. The rock itself is sedimentary, made of clay and silt, exactly the kind of material that on Earth preserves fossils and chemical traces of ancient life. Perseverance's instruments detected organic carbon, sulfur, oxidized iron, and phosphorus, a combination that on Earth often indicates biological activity. But what really caught scientists' attention were small features they call leopard spots, tiny specks enriched with iron phosphate and iron sulfide scattered through the rock like spots on an animal's fur. On Earth, when microorganisms consume organic matter, they often produce iron phosphate and iron sulfide as metabolic byproducts. The pattern of these compounds in chavs resembles what we see in terrestrial rocks that contain fossilized microbial communities. But here is the problem. Chemistry can also create similar patterns without biology. Hydrothermal processes, volcanic activity impacts. All of these can generate iron-rich mineral deposits. The challenge is distinguishing between biological and non-biological origins based solely on chemistry and texture, especially when you're doing it remotely with instruments on a rover millions of kilometers away. This ambiguity is why scientists use the term potential biosignature rather than claiming they have found evidence of life. A potential biosignature is a substance or structure that could have a biological origin, but requires more data or further study before any conclusion can be reached. It is a conservative approach, deliberately cautious, because the claim that we found evidence of extraterrestrial life, even extinct microbial life, is extraordinary and requires extraordinary evidence. The scientific community learned this lesson from past controversies like the announcement in 1996 that a Martian meteorite found in Antarctica contained possible fossils of bacteria, a claim that subsequent research could not definitively confirm or refute. What makes the Chava Falls finding particularly intriguing as the age of the rocks? The Bright Angel Formation is relatively young in geological terms, younger than many of the ancient rocks Perseverance has studied. An earlier hypothesis assumed that signs of ancient life would be confined to the oldest rocks, formed when Mars had a thicker atmosphere and liquid water on its surface. Finding potential biosignatures in younger rocks suggests that Mars might have remained habitable for longer than previously thought, or that habitable conditions returned at later periods. Perhaps volcanic activity periodically warmed the planet, melting subsurface ice and creating temporary oases where life could survive. The sample, officially named Sapphire Canyon after a waterfall in the Grand Canyon, is now one of 30 samples Perseverance has collected and stored in sealed titanium tubes. These samples represent a cross-section of Martian geology, rocks from different eras and environments, each one chosen because it might contain clues about Mars' past. The ultimate goal is to return these samples to Earth as part of the Mars Sample Return Mission. Though that mission faces significant technical and budgetary challenges, bringing samples back would allow scientists to analyze them with instruments far more sophisticated than anything we can send to Mars, instruments that can measure isotope ratios, search for amino acids, examine mineral structures at the atomic scale. Until then, the Sapphire Canyon sample sits in Perseverance's belly, a tiny piece of Mars containing what might be the most important discovery in the history of astrobiology, or might be nothing more than interesting geology. The uncertainty is frustrating, but also thrilling. We are living in the era when the question of whether life exists beyond Earth might finally be answered, not through speculation, but through direct observation. Whether that answer comes from Mars or from the icy moons of Jupiter and Saturn, or from the spectroscopic analysis of exoplanet atmospheres, the search is progressing faster than ever before, driven by technologies that did not exist a generation ago. Some of these technologies, particularly in artificial intelligence, are advancing so rapidly that they are reshaping multiple fields simultaneously. Chapter 7: The Silicon Mind. In 2024, the average company spent $1.9 million on generative AI initiatives. Yet, less than 30% of AI leaders reported that their CEOs were happy with the return on investment. This disconnect reveals something important about where we are in the AI revolution. The technology works, sometimes spectacularly, but translating that capability into business value turns out to be harder than the initial hype suggested. 2025 is the year that reality check is forcing a recalibration, pushing companies to move from experimentation to focused deployment, from asking what AI can do to asking what problems it can actually solve better than existing approaches. The capabilities themselves continue to advance at a startling pace. In September of 2020, 5 researchers at Microsoft announced a breakthrough in protein simulation using an AI-driven system called AI2BMD. Proteins are the molecular machines of life, folding into complex 3-dimensional shapes that determine their function. Understanding how proteins fold and interact is crucial for drug discovery, enzyme engineering, and understanding diseases. But simulating protein dynamics has always been computationally intensive because proteins are large molecules with thousands of atoms, and their behavior depends on quantum mechanical interactions at the smallest scales. AI2BMD allows researchers to simulate these dynamics with unprecedented speed and precision, potentially accelerating the discovery of new drugs and therapies. This is not the only way AI is transforming science. In neuroscience, an AI model called Cell Transformer, developed by researchers at UCSF and the Allen Institute, has created one of the most detailed maps of the mouse brain ever produced, identifying 1/300 regions and sub-regions, including previously uncharted areas. The model works by analyzing massive spatial transcriptomics data sets, essentially mapping which genes are active in which cells and where those cells are located. This allows the AI to identify patterns and boundaries that human researchers might miss, revealing the brain's organization at a level of detail that would take decades to achieve manually. The same AI techniques can be applied to other organs and tissues, including cancerous tumors, opening new avenues for understanding disease and developing treatments. Another AI breakthrough came from University College London, where researchers developed an algorithm that can identify different types of brain cells based on their electrical signatures with 95% accuracy. For decades, neuroscientists could record the electrical activity of neurons, but could not determine what type of neuron they were recording from without using genetic markers or staining techniques. This new approach uses AI to recognize subtle patterns in the electrical spikes that different types of neurons produce, essentially teaching a machine to read the neural code. The implications for brain-computer interfaces and treatments for neurological disorders like epilepsy are significant, though as the researchers caution, there is still a long way to go before this becomes a practical clinical tool. But AI is not just accelerating research, it is becoming embedded in everyday tools and workflows. In 2025, Gartner predicts that 75% of enterprises will transition from AI pilots to full-scale operations, a massive scaling of data infrastructure and analytics, AI agents, autonomous or semi-autonomous software entities that can perceive their environment, make decisions and take actions are moving from concept to reality. These are not the chatbots of 5 years ago limited to scripted responses. These are systems that can handle complex tasks like analyzing legal contracts, managing supply chains, writing and debugging code, even providing personalized medical advice. The rise of AI agents raises questions that go beyond technology. If an AI agent makes a mistake that causes harm, who's responsible? The developer, the company deploying it, the user who relied on it. In late 2025, a lawsuit in Colorado highlighted these issues when parents claimed that an AI chatbot had contributed to their teenager suicide by simulating emotionally manipulative conversations. The case could become a landmark in determining liability for AI systems and the ethical obligations of companies that create them. As AI becomes more capable and more integrated into sensitive areas like mental health, education, and personal relationships, society will need to grapple with questions about trust, accountability, and the appropriate boundaries for artificial intelligence. There is also the question of how AI itself will evolve. Current large language models are trained on vast amounts of text scraped from the internet, learning patterns in language that allow them to generate coherent and often useful responses, but they do not understand what they're saying in any deep sense. They lack common sense reasoning. They make factual errors. They can be tricked by adversarial inputs, and they sometimes produce outputs that seem confident but are completely wrong. A phenomenon called hallucination. The next generation of AI systems will need to address these limitations, incorporating better reasoning, the ability to verify their own outputs, and perhaps some form of understanding that goes beyond pattern matching. Some researchers believe the path forward lies in combining different types of AI, what is called composite AI. Instead of relying on a single large model, you build systems that integrate multiple specialized models, each good at a particular task, along with traditional software and databases. Others think the breakthrough will come from better training methods, or from integrating AI more closely with robotics, giving it a body and sensory feedback so it can learn about the physical world the way humans do. And there is growing interest in neuromorphic computing, building chips that mimic the structure of biological brains, potentially offering more efficient and capable AI than current approaches. Whatever direction AI takes, it is clear that we are still in the early stages of understanding what this technology can and cannot do and what it means for society. The excitement is justified, the potential is real, but so are the challenges and risks. As we develop more powerful AI, we also need to develop the wisdom to use it responsibly. That same need for wisdom applies to another area where our fundamental understanding of reality might be shifting: the mysterious components that appear to make up most of the universe. Chapter 8. The Illusion of Darkness. For nearly a century, cosmologists have believed that the universe is mostly made of things we cannot see. Ordinary matter, the stuff of stars, planets, and people, accounts for only about 5% of the universe's total mass energy. Another 27% is dark matter, invisible but detectable through its gravitational effects on galaxies. The remaining 68% is dark energy, an even more mysterious force that appears to be accelerating the expansion of the universe. Together, dark matter and dark energy dominate the cosmic budget, shaping the structure and fate of everything that exists. But what if they do not exist at all? In October of 2025, a paper by Rajendra Gupta, an adjunct physics professor at the University of Ottawa, proposed a radical alternative. Instead of filling the universe with invisible particles and unexplained energies, Gupta suggests that the fundamental forces of nature, things like gravity, are slowly weakening as the universe ages. If this is true, then the phenomena we attribute to dark matter and dark energy might be illusions, artifacts of using constant laws of physics to describe the universe where those laws are gradually changing. The idea is both simple and profound. We assume that the strength of gravity today is the same as it was 1 billion years ago, and will be the same 1 billion years from now. But what if that assumption is wrong? What if gravitational attraction was slightly stronger in the past and will be slightly weaker in the future? Such a change could make distant galaxies rotate faster than we expect based on visible matter alone, mimicking the effect of dark matter. It could also make the universe's expansion appear to accelerate over time, mimicking dark energy. In this model, you do not need exotic invisible substances. You just need time-varying constants, a universe where the rules change gradually as space itself evolves. This is not the first time someone has proposed modifying our laws of physics to eliminate the need for dark matter and dark energy. Modified Newtonian dynamics, or MANDY, has been around for decades and can successfully explain the rotation curves of galaxies without invoking dark matter halos, but Mont struggles to explain observations on larger scales, like the way galaxy clusters behave, or the patterns we see in the cosmic microwave background. The afterglow of the Big Bang. Gupta's approach, which he calls CC plus TL, attempts to provide a unified explanation for both the cosmological scale where dark energy seems to operate and the astrophysical scale where dark matter seems necessary. By introducing a parameter that varies with both time and the local density of matter, he can reproduce the observed rotation curves of galaxies and the accelerated expansion of the universe without adding any new substances. The timing of this proposal is interesting because it coincides with other observational hints that something might be off with our standard cosmological model. Data from the Dark Energy Spectroscopic Instrument, or DESI, released in April of 2025, suggests that dark energy may not be constant after all. Instead, it might be weakening over time, evolving in ways that the standard model cannot easily explain. If dark energy is changing, then we need to revise our theories. And once you start revising, it is worth asking whether dark energy, as we currently conceive it, exists at all. Meanwhile, experiments searching for dark matter particles continue to come up empty-handed. The Lux Zeppelin detector, the most sensitive dark matter detector ever built, has been running for years and has found nothing. It has set stringent limits on the properties that dark matter particles, if they exist, must have, progressively ruling out vast swaths of theoretical possibility space. Each null result makes the remaining options for what dark matter could be more exotic and less probable. Some physicists are starting to wonder whether we are searching for something that is not there, like ancient astronomers adding more and more epicycles to try to make the geocentric model of the solar system work. But abandoning dark matter and dark energy is not easy because they explain so much. They explain why galaxies rotate the way they do, why galaxy clusters hold together, why gravitational lensing occurs where it does, why the cosmic microwave background has the pattern of hot and cold spots that we observe. Any alternative theory needs to explain all of these phenomena, at least as well as dark matter and dark energy do, preferably better. Gupta's model is a step in that direction, but it will need to survive rigorous testing against the full range of cosmological data before it can be taken as a serious competitor to the standard model. What makes this debate so fascinating is that it touches on the most fundamental question in science. How do we know what is real? Dark matter and dark energy have never been directly detected. We infer their existence from gravitational effects, from the motion of visible matter, from the structure of space-time. But inference can be misleading. For centuries, astronomers believed that planets moved in perfect circles because circles were the most perfect shape. The truth turned out to be ellipses, a simpler solution once you stopped assuming perfection. Could we be making a similar mistake now, assuming the universe contains exotic substances, when the reality is that our equations need adjustment? The answer will come from more and better data. The Vera C. Rubin Observatory expected to begin observations later, in 2025 or early 2026, will survey the sky with the largest digital camera ever built, imaging billions of galaxies with unprecedented detail. The data it collects will test dark matter and dark energy models with a precision that current experiments cannot match. Similarly, the Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will measure the universe's expansion rate and map the distribution of matter on cosmic scales. Between these new instruments and ongoing experiments, the next few years should clarify whether dark matter and dark energy are real, or whether we need a fundamental thinking of cosmology. Either way, the process reveals something beautiful about science. It is never finished. Every answer opens new questions. Every certainty eventually meets a challenge. And sometimes the most revolutionary discoveries come not from finding something new, but from realizing that what we thought we knew was incomplete. Chapter 9. The Space Between. While scientists debate the nature of the cosmos and engineers build quantum computers and fusion reactors, another quieter revolution is happening in how we venture beyond Earth's atmosphere. On October 8, 2025, Blue Origin launched its 15th space tourism mission. The passengers aboard experienced a few minutes of weightlessness, saw the curve of the Earth against the black of space, and returned safely to the ground. For them, it was likely a transformative experience, the kind of perspective shift that astronauts call the overview effect. For the space industry, it was business as usual, another successful flight in what is becoming a routine commercial operation. This normalization of access to space feels significant when you step back and consider the broader picture. A generation ago, spaceflight was the exclusive domain of government agencies and professional astronauts, people who trained for years and underwent rigorous selection processes. Now, private companies are flying, paying customers, and while the price tag remains prohibitively expensive for most people, costs are dropping as technology improves and competition increases. SpaceX has revolutionized launch with reusable rockets, dramatically reducing the cost of putting payloads into orbit. Blue Origin is working on its own reusable systems. Other companies are developing space planes, orbital hotels, lunar landers, and Mars mission concepts. The infrastructure being built today is not just for tourism, it is laying the groundwork for a future where humanity is a multiplanetary species. SpaceX's Starship, the largest and most powerful rocket ever built, is designed to carry cargo and eventually people to the Moon and Mars. NASA's Artemis program plans to return astronauts to the lunar surface, establishing a sustained presence that will test technologies needed for longer missions. China is building its own space station and has announced plans for a lunar base. India, Japan, and several European countries are developing their own spacefaring capabilities. All of this activity raises questions about what we will do once we get there. Space is not a forgiving environment. There is no air, no water, extreme temperature swings, radiation from the sun, and cosmic rays. Building habitats that can sustain human life will require solving problems in life support, agriculture, manufacturing, and medicine. We will need to extract resources from asteroids, the Moon, or Mars itself, because launching everything from Earth is impractical for long-term settlement. We will need energy sources, likely solar power supplemented by small nuclear reactors, and we will need to address the psychological challenges of isolation, confinement, and distance from Earth. But perhaps the biggest question is why we should do this at all. The pragmatic answers include resource extraction, scientific discovery, and ensuring the long-term survival of humanity by spreading beyond a single planet vulnerable to asteroid impacts, supervolcanoes, or other existential threats. The more aspirational answers point to human curiosity and the drive to explore. The same impulse that sent our ancestors out of Africa to populate every continent, that pushed explorers across oceans, that drives scientists to peer ever deeper into the mysteries of nature. Space represents the ultimate frontier, not because it is empty, but because it is vast and largely unknown, full of possibilities we can barely imagine. And space exploration does not happen in isolation from the science and technology we've been discussing. Quantum computers might one day optimize spacecraft trajectories or enable new forms of communication across interplanetary distances. Fusion reactors could provide the power needed for fast propulsion systems that reduce travel time to Mars from months to weeks. AI will be essential for managing the complexity of life support systems, navigating autonomously and analyzing the massive amounts of data collected by sensors. The search for biosignatures on Mars or the moons of Jupiter informs how we think about where and how to look for life beyond Earth. Everything connects. The universe is not made of isolated parts, but of relationships. Patterns that repeat at different scales, principles that apply across domains. A comet's chemistry tells us about planet formation. The quantum computer's behavior reveals fundamental truths about reality. A fusion reactor mimics the processes happening in stars. A brain-mapping AI shows how complexity emerges from simple rules. And a private spaceflight company makes it a little more possible for humans to become citizens of the solar system, rather than residents of a single planet. These connections matter because they remind us that progress is not linear. It does not happen in one field at a time, neatly compartmentalized. It happens through cross-pollination, through ideas developed in one context finding unexpected applications in another, through teams of people from different disciplines working together on problems too complex for any one perspective to solve alone. The breakthroughs of 2025 in quantum computing, fusion energy, Mars exploration, AI, cosmology, neuroscience, and space access are not separate stories. They are chapters in a larger narrative about human capability and curiosity. Chapter 10: The Horizon. We began with an asteroid that passed unnoticed in the night and a comet brightening in the October sky. Two reminders that the universe is dynamic and that our place in it is both small and significant. We looked at a distant planet forming moons from a disk of gas and dust, a process that echoes how our own moon came to orbit Earth billions of years ago. We saw quantum computers reaching a level of sophistication where they might soon solve problems beyond the reach of classical computing and fusion reactors, maintaining plasma long enough to hint at a future powered by the same reactions that light the stars. We examined a rock on Mars that might contain evidence that life once existed beyond Earth, though the question remains open and will likely remain so until we can analyze that rock in laboratories here at home. We watched artificial intelligence map brains, simulate proteins, and raise new questions about autonomy, responsibility, and what it means to be intelligent. We considered proposals that dark matter and dark energy, the invisible substances thought to dominate the cosmos, might not exist at all, that the universe we think we know might be based on incomplete equations, and we noted that space travel is quietly becoming more accessible, not yet commonplace, but moving in that direction step by incremental step. Each of these developments carries uncertainty. Quantum computers might hit unexpected obstacles that delay their practical deployment. Fusion reactors might prove harder to commercialize than optimists hope. The Martian biosignatures might turn out to be geological rather than biological. AI might plateau or require breakthroughs we have not yet conceived. Alternative cosmologies might fail to explain observations as well as dark matter and dark energy do, and space exploration might remain expensive and dangerous, the domain of governments and billionaires rather than ordinary people. But uncertainty is not the same as futility. It is the space where discovery happens, where our understanding grows, where we test ideas against reality and revise them when they fall short. Science is not a collection of facts. It is a process, a way of asking questions and refining answers. And the questions we're asking now are among the most profound ever posed. What is the universe made of? How did life begin? Can we harness the power of stars? What is consciousness? Are we alone? How do we ensure that the technologies we create benefit rather than harm us? These questions do not have simple answers. And that is okay. If they did, they would not be worth asking. The value lies in the search itself, in the knowledge we gain along the way, in the technologies we invent to probe deeper, in the way our perspective shifts as we learn more. 100 years ago, we did not know the universe was expanding. 50 years ago, we'd not visited Mars with rovers or discovered planets around other stars. 25 years ago, quantum computers were laboratory curiosities, and AI could barely recognize handwritten digits. The pace of change is accelerating, driven by compounding advances in computing materials, instrumentation, and understanding. What will the next decade bring if fusion becomes commercially viable? Energy abundance could transform civilization, lifting billions out of poverty and enabling projects that currently seem impossible. If quantum computers mature, they could accelerate drug discovery, material science, and cryptography, reshaping industries and geopolitics. If we confirm biosignatures on Mars or detect them in the atmosphere of an exoplanet, it would be one of the most significant discoveries in human history, proof that life is not unique to Earth. If AI continues to advance, it could become a partner in scientific research, generating hypotheses, designing experiments, analyzing data at scales beyond human capability. And if space access continues to democratize, the resources and knowledge of the solar system could become part of the human commons, available to future generations in ways we can only begin to imagine. But these possibilities also come with risks. Technologies are tools, and tools can be used for good or ill. Quantum computers could break the encryption that protects everything from bank accounts to military communications. Fusion, if weaponized, could create devastation. AI could reinforce biases, eliminate jobs, or be deployed in ways that reduce rather than enhance human flourishing. And space exploration, if pursued carelessly, could spread contamination, destroy irreplaceable scientific sites, or exacerbate inequalities. Navigating these risks requires more than technical skill. It requires wisdom, ethics, foresight, and a willingness to consider not just what we can do, but what we should do. It requires diverse voices in decision-making, transparency about risks and uncertainties, and humility about the limits of our understanding. The scientists and engineers pushing the boundaries of knowledge are acutely aware of these responsibilities, even if public discourse sometimes treats technology as either a savior or a threat with no middle ground. The truth is more nuanced. Technology is neither good nor bad in itself. It amplifies human intentions and capabilities. In the right hands, with the right goals, it can solve problems, reduce suffering, and expand possibilities. In the wrong hands, or with short-sighted goals, it can cause harm. The challenge is to build systems, institutions, and cultures that steer toward the former and away from the latter. And that challenge belongs to all of us, not just to scientists and policymakers. So, here we are in October of 2025 watching comets brighten, reading about quantum entanglement, learning of plasma records and potential biosignatures. The universe continues its ancient dance. Stars forming and dying, galaxies colliding, comets plunging sunward, moons coalescing from dusty disks. Life, at least on one small blue world, has learned to look outward and ask questions, to build tools that extend our senses and understanding, to dream of futures where the boundaries of the possible expand beyond recognition. Thank you for joining me on this journey through the latest discoveries and breakthroughs. If you enjoyed this exploration, consider leaving a like and subscribing to stay connected as science continues to reveal the universe's secrets. The work of understanding our cosmos never stops, and every answer we find opens doors to new mysteries waiting just beyond the horizon. As always, all information shared here is for educational purposes based on current research and understanding, which continues to evolve. Keep looking up, keep asking questions, and remember that we are all part of this grand unfolding story. Until next time, wherever you're listening from, whatever time it is, good night.